Yeah, thanks for the introduction. Hi everyone, my name is Zhuqi, and today I'm going to present our recent work, Dashlet, Taming swipe uncertainty for robust short video streaming. This work is finished when I was a PhD student at Princeton University under collaboration with Professor Yaxiong, Ravi, Netravali, and Kyle Jamieson. Short video streaming apps like TikTok, YouTube Shorts, and Instagram Reels are gaining popularity recently. They are consistently ranked among the most downloaded apps in the App Store, and the users are spending increasing amount of time on those kind of short video applications. Due to the popularity, so a large volume of network traffic will be used to send those kind of short video data. And so it makes this kind of problem an important question for us to answer. So there are a lot of existing work on video streaming over the past decades. But those previous works all focus on traditional video streaming. So the key difference for short video streaming is users can seamlessly switch to the next video with a simple swipe on the phone screen, so based on their interest. So those kind of swipe can cause two key differences for short video streaming compared with the traditional one. The first one is some parts of the content might be skipped. In addition, due to the sudden switch caused by the swipe, the video chunks are not always played sequentially. So this kind of effect is not actually modeled by all those previous video streaming algorithm. To handle this issue, we actually need a new design to solve the short video streaming problem. So intuitively, an ideal way to download the video chunks for short video is the algorithm should buffer some videos chunks out of order. Like for this example, if the algorithm buffers some chunks at the beginning of video 2 and video 3, rebuffer will not happen when the user swipes to new videos. Unfortunately, all the previous traditional video streaming algorithm assumes that they buffer the video sequentially. When the user swipes happens, so when the user swipe happens, the downloaded chunk in the previous video will be totally wasted. At the same time, rebuffer also happens, since the first chunk of the next video is not downloaded yet. So the video playback has to pause until the next video chunk is fully downloaded. So both the wasted download and the rebuffering have a very significant negative impact on the user's watching experience. Before designing our own short video streaming algorithm, we first take a look at how the state-of-art system works. So specifically, we choose TikTok as our baseline system to study. So TikTok is the most popular short video streaming application in the world. So we reverse engineer the TikTok buffering logic by recording an HTTP request between the TikTok app and the server with a man-in-the-middle proxy. So we summarize how TikTok works with 3 bullet points. First, TikTok actually uses 1 megabyte as a threshold to split a video into 2 chunks. The first chunk is the first 1 megabyte data, and the second chunk is the remaining data. And the second, TikTok will pre-buffer future first chunk videos, but we'll only start to download the second chunk video when the current video starts to play. When the user swipe happens, TikTok will prioritize the download of the current video's second chunk over the future video's first chunk. As we can see that TikTok partly overcomes the problem of traditional video streaming algorithm. The 1 megabyte chunk at the beginning of every video reduces the chance that the buffer is empty when the user swipe happens. However, on the other hand, TikTok's solution still has its own problem. Specifically, the algorithm is vulnerable to various swipe patterns. For example, if the user swipes early in video 2, the second part of video 2 is then completely wasted. If unfortunately network also becomes bad at this moment, the rebuffering also happens since the second chunk of video 3 is not downloaded yet. The key problem behind that is TikTok actually uses the fixed pre-buffering rules and does not adapt to the user swipe pattern. So without this kind of adaptation, the problem of wasted download and the rebuffer will frequently happen. So to understand how user swipe, or to understand the user swipe pattern, we collect two user swipe datasets. One is the smaller college student datasets with 25 participants and around 3,000 swipes. So we developed a mobile web-based short video streaming service to collect the data, and the figure on the left shows the interface. Another dataset is collected through Amazon Merck over the 1,000 participants and around 0.1 million user swipes. The figure on the right shows the corresponding data collection interface. So to figure out if there's any pattern to the user swipe, we plot the distribution of the data sets. The figure on the left shows the figure shows the example distribution for 4 different videos. For the college student data sets, we can see that the user swipe pattern among different videos is actually quite different. However, when comparing the user swipe distribution between 2 data sets, we can find that the swipe distribution is relatively stable across different data sets. That's to say, we can collect the swipe distribution for each video and then use them as an indicator to help the algorithm decide the buffer order. Before introducing how Dashlet decides the buffer order, we first take a look at how the buffer order is decided in traditional video streaming. Actually, such an order is determined by the playing start time. Specifically, the video chunk that will be played early should be downloaded early. In traditional video streaming, the playing start time of the chunk is monotonically increased. Therefore, the video player can simply choose the video chunk with the earliest playing start time as the next one to download. For short video cases, the playing start time is not monotonically increased anymore. It's actually become a random variable. For example, the playing start time for the second chunk of video 3 will depend on the user swipe time on video 1 and 2, as well as the duration of its previous chunk in video 3. Since the user swipe time is a random variable with video-specific distribution, therefore, the playing start time for a chunk will be also a random variable, since it includes the summation of one or multiple user swipe time. Given the swipe distribution, we can then mathematically calculate the playing start time for each video chunk. So the Dashlet algorithm actually follows the same idea of determining the buffering order based on the playing start time of video chunks. Specifically, it includes 2 steps. First, we calculate the playing start distribution for all candidate chunks that we need to buffer. And then, we use a heuristic algorithm to rank the priority among those chunks. Please refer to the paper for more details about our algorithm. For Dashlet prototype, we implement a short video player by modifying a traditional video player called dash.js. In addition, we implement Dashlet's algorithm to schedule the download order. We evaluate Dashlet by comparing with TikTok to make a fair comparison and also reflect the real user scenarios. We first recruit volunteers to use TikTok under a controlled network environment to get the quality of experience in the real TikTok app. At the same time, we record all the videos and that user watched and the corresponding swipe timestamps. Then we replay those user watching trace to evaluate the dashlet on exactly the same video, the same swipe traces, and the same network. So here's the result. In the we compare Dashlet with TikTok Android app. In addition, we add an Oracle baseline as a reference. We assume that the Oracle baseline knows the exactly swipe time when the user swipe in the future, and the average throughput during the future lookup window. So it then serves as the upper bound for any short video streaming algorithm. So we present the result on 3 network throughput cases. We first show the end-to-end result on QoE. QoE is a metric that considering both the bitrate reward, rebuffering penalty, and the smoothness penalty. The red bar is the result for TikTok. And we show the result for Dashlet. We can see that Dashlet improves the average QoE over TikTok by 101%, 64%, and 28% on different network throughput cases. At the same time, the QoE also have a much lower variance compared with TikTok. In addition, we can see that the QoE of Dashlet is actually very close to the Oracle baseline. We also present the result on different factors that impact the QoE. The first is rebuffering. In the figure, the y-axis is a percentage of time that is under rebuffering during all the watching sessions. And we also see a significant improvement for Dashlet over TikTok. Then we present the result on bitrate reward and the smoothness penalty. By comparing the scale, we can find that the smoothness penalty is generally small, and the majority difference between the Dashlet and TikTok is due to the bitrate reward and the rebuffering penalty. Dashlet is significantly better on TikTok on both factors. In addition, we can see that Dashlet achieved to close to optimal performance starting from 6 Mbps, while TikTok does not achieve that even at 12 Mbps network throughput. We also present some baselines, we also present the result in terms of the data wastage and network idling as a micro benchmark. So data wastage is the percentage of the video data that is downloaded but not watched by user. In the figure, the boxes spans 25 percentile and 75 percentile of the data, and the black line spans the mean and the max of the data. The intersection between two lines is the median of both data wastage and the network idling percentage. The Oracle baseline has 0 data wastage because it knows the future swipe timestamps, and then will not download chunks that is not watched. By comparing Dashlet and the TikTok, we can find that Dashlet can reduce the median data wastage percentage from 38% to 29%, and reduce the network idling percentage from 61% to 45%. So to conclude this talk, we design and implement Dashlet system with 2 following insights. First, user swipe is a critical information for short video streaming to decide the buffer order. Second, video-specific swipe distribution is a powerful tool to achieve a high QoE. We evaluate Dashlet by comparing with TikTok app, and Dashlet can improve the QoE by 28 to 101% respectively. And we open source the code at GitHub. Please check it out if you like. And with that, I would like to take any questions.